Okay, let's end this week with another footnote in Femboy theory. It's all about manifolds today, because my primary description of manifolds are it's a bit inaccurate because not all manifolds can be squashed down onto R in space. And in fact, the real definition of a manifold is that it is locally, a characteristic is that it is locally um, locally resembles R2 space. So in reality, if we zoom in on the surface of a manifold, we should be able to see a flat surface. And that's an example why sphere is a primary example of a manifold. Because if we zoom in on the surface of a sphere, it looks flat. But of course, when we zoom out, we know it's curved and stuff like that. And yeah, that's really what I need to say about manifolds here. But really, they should resemble R2 space. And they are not always, or we cannot always project them onto R space, because some of these guys, some of these manifolds are complex valued, so there's really no function that can map, every point, onto R space. Because okay, take for example C2. C2 is a space, or yeah, C2 is a topological space. So, or actually just C, or the complex plane, which is the set of all points x plus I, y, such that x and y are in real numbers, and I is equal to the square root of -1. This, you can think of this as a manifold. Of course, it's a plane, and then the y plane is the fractions of I. And then this is 1, 2, 3, 4, 5I, and then in the minus direction, and then this is the real component 1, 2, 3, 4, 5, so on and so forth. Now, we can't really project this onto R2. So this is R2 here. There's really no projection we can make from this to here. Though I believe we do, or there is some projection, but it's not very clean, and it may be discontinuous. So that's that. I mean, we can take the square of IY, or we can take the conjugate of this, or the complex conjugate of this, and then sort of multiply it by that. And I suppose that would give us a map to R2, but it's not really that clean, because when we're dealing with topological space, we want maps to be very clean, right? And yeah, there's a homotopy between these two. These guys are homotopic to each other, but that's really what we should only care about when it comes to C and R2. So if we make a curve here, so just C itself, if we make a curve in it, say like this, I'll call it gamma. And then I have another curve here, which I will also call gamma, but I'll name it gamma 2. These two curves are homotopic to each other. We can probably map this onto here, but it's very difficult to do that. Because this is an inherently complex valued function, which technically comes from another space. So it's some C mapped onto C. Or the unit interval 1 minus 1 mapped onto C. Sorry. So gamma really maps the interval 0, 1 onto C. So that's an important distinction I had to make. This important footnote is that, of course, not all manifolds can be projected onto R, and that really they are surfaces or curves that locally resemble R in space. So if a manifold is of n dimension, when we zoom in on a manifold, we can see n minus 1 R space. So if we have a surface, of course, a sphere, that's three-dimensional, right? When we zoom in, all we see is a flat space. So it's two-dimensional space, so R2. And then, of course, for some one-dimensional point, like or one-dimensional manifold, like a line or an interval, when we zoom in, we only see a point, so it's really R0. So that's really what I missed when I defined manifolds here. So we think of this really as just a collection of points. So a collection of attributes from O or P, and then we just sort of collect them all together into one continuous line. Not really discrete, but we can think of it as discrete sometimes. So that's what I didn't explain about manifolds during my discussion of manifolds. So that's it for the short footnote.